this video, we are going to discuss free fall. Free fall occurs when the acceleration or deceleration is due to the force due to gravity alone. So there are no other forces acting on the object as it is moving through the air. So the previous problem, hopefully you did the previous example problem, where there's a rocket attached, that would not be a free fall problem because there's a rocket attached. There's thrust from the rocket, so the object is not in free fall. In free fall, the only force acting on the object is the force due to gravity. And what that force due to gravity is, of course, depends upon what object you're on. So if you're on the Earth, you're going to experience a certain free fall. And if you're on the Moon, you're going to experience free fall a little differently. Not differently in the laws of physics, but differently than the force, and thus the acceleration is going to be a little bit different. Now I do say flying through the air because we're used to there being air in our surroundings, but in fact we're going to ignore the fact that there is air. Because if you think about it, if you drop a bowling ball and you drop a feather, the bowling ball is going to hit the ground before the feather. So it seems like the mass of the object matters. However, what's going on is that the feather is experiencing friction or air resistance or drag, a lot of vocabulary words for this, that the bowling ball is not experiencing as much of. So there's another force in the system. So that means for all problems, let's see, no rocket engines, and we're going to ignore air resistance. We'll explore including air resistance a little bit later in the semester when we talk about conservation of energy. The acceleration that the Earth causes as an object within Earth's gravitational field, we're going to assume for now is 9.8 meters per second squared. We're going to assume it's a constant value. We'll learn later on in the semester how to calculate how the value changes based upon being on another planet or based upon the distance from the surface of the Earth. But for now, we're going to assume we're near Earth's surface and that the acceleration of gravity is 9.8 meters per second squared. However, keep in mind that this value would be negative. And I don't automatically put the negative sign on the 9.8 because there's going to be equations later on in the semester where we're going to want to plug in a positive 9.8. But for now, we're going to always plug in a negative 9.8 meters per second squared. And this is regardless of whether you're going up in the positive y direction or coming down in the negative y direction. It's always going to be negative because the force due to gravity acts in the negative y direction. So the Earth's mass is always pulling us towards its center. It's not pushing us away from the surface. It's always pulling us down towards the center, which we defined as negative y. Alright, so let's talk about this a little bit more conceptually. So we have the ground, and we have a person, and let's see if I can draw a person stick figure reasonably. And the person throws the ball up in the air, so it has some sort of initial velocity. And as the ball goes up, because the acceleration to gravity is negative, it's a deceleration. So this is going to be a deceleration. The velocity decreases. And it's going to decrease until the velocity equals 0. Because once it's equal 0, you have no more speed to go upward with. There's no increase in distance anymore. And the displacement, when that velocity equals 0, is referred to as max height. So if I asked you what the max height is, you would set velocity final to 0 and solve for the displacement. It does not mean that the displacement is 0, because that would not make sense, because it means the ball never left the person's hand. Now, once it's reached 0 velocity, it's going to come back down, because remember, the Earth is always pulling on the object. So now you're going to start at 0 velocity, and you're going to head back downward. Now, this is where we have to remember where minus signs for velocity are an indication of direction, not an indication of an absence of something. Like there's a minus sign in your checkbook as you wrote a check that was bigger than your bank balance amount. So here the velocity is increasing in magnitude, but in the negative direction. So this is an experience of negative acceleration. So you're experiencing a negative acceleration because the velocity is increasing, but increasing in the negative direction. And it's going to increase until when it reaches the position that it left, so gets back to the person's hand, it's going to have a velocity that has the same magnitude as the initial velocity, but it will be negative. Now, if it keeps falling, the velocity will become more negative. So the velocity will continue to increase in magnitude, but it'll be in the negative direction. Now be careful when solving problems. We're always talking about the velocity just before it hits the ground. So if it says it hits the ground, it always means the velocity just before it hits the ground. And I try to remember to put that phrasing in problems, but once it hits the ground, it's no longer a constant acceleration problem or a kinematic problem, because now you've introduced another force from the floor. So that's an entirely different type of problem that we're not dealing with yet. So it always is just before it hits something else.